This short video discusses testing hypotheses using test statistics and how test statistics are related to the sample data, alpha levels, and p-values. The discussion is framed at a more conceptual level rather than digging more deeply into the math. In the previous video, we discussed the alpha level as being that line in the sand that we must cross in order to reject the null hypothesis. And the p-value is calculated from our data and used to determine whether we have in fact gone over that line. In essence, the p-value tells us whether the findings from our study are sufficiently extreme, if the null hypothesis were true, that we can conclude it's just too unlikely that the null is true, and we should reject it instead. But where do p-values come from? P-values are determined using what are called test statistics. I suspect that a test statistic is what students generally think about when they think about stats. A good but wordy definition of a test statistic is the following. A test statistic is a number we calculate from our data that is sensitive to whether the null or alternative hypothesis is true. We use the test statistic to determine the p-value, and we compare our p-value to the alpha level in order to reject or fail to reject the null. Now, this is important. Remember that the p needs to be less than the alpha level in order to reject the null hypothesis. So we like small p-values. Now, there are lots of different test statistics depending on the type of data the researcher has and the specific question they're asking. There are T's and F's and Z's and chi-squareds, but conceptually they all basically work the same way. The bigger, meaning more extreme or further from zero, the test statistic, the smaller the p-value and less likely the results are due to chance. For many students, the whole idea of a test statistic may seem a little abstract. Instead of talking about scores on a test, we're suddenly talking about things called a t or a chi-square. These crazy new numbers may not seem to relate to the actual things that we're measuring and may appear to come out of the blue. What does the number mean? Where did it come from? Over the years, I've found that the best way to me to understand what a test statistic is to think about Julia Child.
Using a great big rubber spatula, the chocolate gets folded into these beautiful beaten eggs. I'll refresh your memory on that. That was a pound of chocolate and a quarter cup of rum and a quarter cup of coffee, and folded into 6 eggs that have been beaten with 1/2 cup of sugar. That's very easy. It's a really very easy recipe.
Before getting into the cooking, let's first visually compare 2 possible ways that a study such as this could have turned out. This figure illustrates how the data in our hypothetical study looked. This blue curve illustrates the distribution of test scores in the classroom with the standard math program. And this red curve illustrates the distribution of scores in the classroom that was using magic math. The vertical hashed lines indicate the means for each group. Notice that while the mean for magic math is higher, the 2 distributions are almost identical with a great deal of overlap. In other words, there's a lot of variability in the scores within each group, but relatively little difference in the means. Most people would probably look at this and conclude that whatever difference is seen in the means may well be due to random differences between the groups, rather than magic math truly increasing scores. On the other hand, this figure illustrates the situation where we have much greater differences between the means, with much less variability within the groups. Notice how this looks very different. The 2 distributions don't overlap at all. Most people would probably look at this and conclude that one would not randomly see such a difference very often if the two groups were in fact identical, meaning magic math had no effect. Finally, recall our discussion of the standard error of the mean. The size of the samples also comes into play. With small samples, one random student scoring very high or very low can make a big difference in the mean. With larger samples, the effects of such extreme students tends to get canceled out by other students in the group. Consequently, the larger the groups, the more tightly clustered the expected means for each sample would be, making the differences between those means relatively larger. So determining how large an effect is, or how likely it is that we would have seen an effect or some difference if the null hypothesis were true, depends on a lot of different numbers. How big is the difference that we saw? But we know that interpreting that depends on how much variability there is in the data. Small variability makes differences between means appear relatively larger. Plus, there's the variability in the means, our standard error of the mean. We know that depends on the sample size. Larger sample sizes leads to less variability in the expected means. How does one integrate all of this, all of these numbers, in order to decide whether to reject or fail to reject the null hypothesis? So, where does Julia come in? The Julia Child approach says to think of these descriptive statistics, the mean, the variability, the sample size, as ingredients in a recipe. If we're making a cake, you may have eggs and milk and flour. Each is useful on its own, but limited. But when you mix them all together and put it in the oven, let it bake a little while, out comes a chocolate cake. We've combined those bland raw ingredients of eggs and milk and flour, and out comes something completely different, a tasty cake. We can think of a test statistic as a cake we bake by mixing together information about means and variability and sample sizes and other stuff. Inferential statistics takes all this information, mixes it together, puts it in the oven to bake for a while, and out pops a t-test cake or an f-test cake or some other type of statistical test cake. From this perspective, hypothesis testing is kind of like a bake-off. In a bake-off, a chef mixes together the eggs and flour and milk in order to create a cake. Judges then taste the cake and decide if it wins a ribbon. With hypothesis testing, a researcher mixes together the mean and the sample size and measures of variability in order to create a test statistic cake. They then have it judged using a p-value and decide whether it wins the ribbon, meaning you can reject the null hypothesis. Note that in a real bake-off, judges don't go and taste the raw eggs or the flour. Once the cake is baked, the cake becomes the focus. Similarly, once the researchers bake a test statistic cake, the test statistic becomes the focus. The key is that the test statistic is something new that's created from all the descriptive statistics being mixed together. But the test statistic then becomes the focus of the hypothesis testing, and it's the test statistic that then gives you the p-value. We'll explain this in more detail in the next video on one-sample z-tests, but for now, the bigger the test statistic, meaning the more extreme it is, the further it is away from zero, the more extreme the results are, assuming the null hypothesis is true, and the smaller the p-value will be. So again, our next video series uses a statistical test called a one-sample z-test to show how a test statistic can be calculated and used to determine the p-value, which is then compared to the alpha level in order to decide whether to reject or fail to reject the null hypothesis. In the meantime, if you're reading a research article and confused as to what a t or z or f or chi-square is and how it's related to the actual data, think of Julia Child using the raw data to bake a test statistic cake, which the researcher judges with a p-value and hopes will be awarded a reject the null hypothesis blue ribbon.
So that's all for today. This is Julia Child. Bon appetit.